Okay, so here's our surface. We'll call that the x direction. Here we are at x equals 0. Here we are at x equals 2. Here we are at x equals 4. And we have some v naught, some v2, and some v4. Okay, so these are the speeds of the particle at x equals 0, at x equals 2 meters, and at x equals 4 meters. And the work that we're going to do on it looks like this. Here's the force as a function of x, and it goes like this. Started up here at 10. It went all the way down to minus 10. This is x equal 2. This is x equal 4. And that, of course, is x equals 0. Okay, and let's write down some givens. So the givens are going to be the mass of the box. And we can use my numbers here, 1.6 kilograms. And then they also give us the velocity initially. So v naught is 5 meters per second. What we're looking for is the velocity at x equal 2 and the velocity at x equal 4. So let's take a guess, just right off the bat. If this box comes in at v naught, is v2 going to be faster than v naught or smaller than v naught? Bigger or smaller than v naught? Okay, why do you say smaller? Because this force is decreasing, right? It's got sort of a negative slope. All right. But is the force in this region to the right or to the left? It's to the right. Even though it's decreasing, it is positive in that whole region. And so V2, is it going to be going faster or slower? Let's say it's going to be faster. That's our guess. What about in this second region? What direction is the force in the second region? It's a negative, and so it's to the left. And so V4, how is it going to compare to V2? It's got to slow back down, right? V4 is less than V2. Those are our guesses in pink. So now let's see if we can figure out exactly how to do this. One thing we know that we just talked about is work goes into a change in kinetic energy. Okay. How do we calculate work in this case? Work, W, is going to be the integral of f dot dx. But we know what f dot dx is. That is f cosine theta times dx. But f cosine theta, that is the x component of the force. And so all this simplifies to that. Okay, what's the work? It's that. So now let's break it up into sections. So let's go from x equals 0 to 2. In that x equals 0 to 2 region, I can say the work going 0 to 2 is equal to the integral from 0 to 2 of f sub x dx. So what is an integral? What's another way to think about an integral? area under the curve. So we could either figure out what that functional form is and do an integral, or we could just say this is the area under the curve. Which in this case, it's just a triangle, right? So it's a half the base times the height. So it's 1/2 the base, which is 2, times the height, which is 10. And so we just get 10 joules. That's this first part right here. What about the second part? Let's do x equal 2 to 4. Work 2 to 4 is going to be the integral from 2 to 4 of f sub x dx, which again is just the area under the curve here, which is 1/2 the base times the height. So it's 1/2 the base, which is 2, times the height, which is -10. And so we get minus 10 joules. Okay, so now we know what the work is for those two sections. Let's see if we can relate it back to the kinetic energy. So delta K is K at the final position, which we'll say is at 2, minus K at the initial position, which is 0. And all of that has to equal the work, which for that section is just 10 joules. But we know what this is. This is 1/2 mv2 squared minus 1/2 mv0 squared is going to equal 10 joules. And now we can solve this for V2, right? Multiply everything by 2, divide by m. I get V2 squared minus V0 squared equals 2 times 10 over m. I can move V0 over to the other side. I get V0 squared plus 2 times 10 over m. And I have to take that square root. And we have all those numbers. So let's plug them in. V0, what did we have for V0? Was it 5? 2 times 10 divided by m was, what was m? Yeah, 1.6. So somebody punch that into your calculator, tell me what you get. I'll see if I can approximate it here. So this is 25 plus 20 over 1.6 has got to be about 12. Maybe a little bit more, 13, let's say. So this is square root of 38, which is pretty close to 6. So we'll say a little bit more than 6. I'm going to say 6.1. Anybody get a real answer for that one? 6 point what? 6.12. All right, so our guess was pretty good. All right, 6.12 meters per second. I got my homework sitting right here. Let's try it, see if we get the green light. 6.12 meters per second. Indeed we did. Got the big happy green light, which is cool. Don't you feel so vindicated when you get that? I know, it's like, am I going to submit? Am I going to submit? I'm not sure. Okay, so that was part. The initial velocity was 5. We applied some force and ramped it up to 6.12. But now we're going to apply a force in the other direction, so it's got to slow back down. But what does it slow back down to? Somebody's saying 5. Why 5? Five is the correct answer. Why is it the correct answer? Because we did 10 joules of work in between 0 and 2, But then we did minus 10 joules of work in between 2 and 4. So I've added 10 joules, and then I've subtracted 10 joules, and so I have to be exactly where I started from, 5 meters per second. Let's plug it in and see. Correct. All right, we are golden.